Good morning from Toronto, Canada. Good morning, good afternoon, good evening, depending on where you're joining us from. Thank you very much and welcome to today's webinar. My name is Pasha and I'll be your host and moderator this morning. And as you might have heard, today we have a very exciting presentation which will be given by my good colleague and the Chief Operating Officer of Quanser, Mr. Paul Karam. Just a bit of a background on the webinar. We are almost a quarter through the 21st century, yet self-driving cars are still in their infancy. Paul will start this webinar by asking some intriguing questions about the future of self-driving technologies, and he will cover the investments required for infrastructure, whether physical, virtual, or mixed, as well as the necessary architectures for researchers to take full advantage of the age of the smart car. Just a bit of background on Paul himself. Paul has spent the last 10 years leading our engineering team, where he drives innovation in key emerging applications, including autonomy, artificial intelligence, and self-driving cars. In the recent months and in response to the current global pandemic, Paul has led a large group of R&D engineers to create a suite of virtual lab experiences with digital twins of classic Quanser hardware that allow professors offer meaningful, engaging, and exciting engineering lab experiences in the areas of controls, robotics, and autonomous vehicles. And with that, I'll pass it over to Paul to start today's webinar.
All right, thank you so much, Pasha, for that introduction and getting us started here. Welcome to all our participants from around the world. I will start to share my screen here. There we go. All right. So thank you once again, and good morning, good afternoon, and good evening for all of you joining us from across the world. And we are very, very happy today. And the topic of today will be mixed reality with a Quanser Q car. And just to give you some background, what I'm going to be showing is the evolution of our self-driving car studio. We released this self-driving car research studio just before the pandemic swept over the world in February 2020. And as a result, even through the challenges of the pandemic, we've had a lot of great success with a lot of our partners and customers adopting this research studio to really push the boundaries and push the envelope of the research around all things autonomous, specifically around self-driving cars and their technologies therein. So hopefully you'll get a good insight into where Quanser is heading, where we are evolving our research studio around this exciting field of autonomous systems and self-driving cars, and more specifically, as a result of the pandemic, how we are also taking advantage of digital twin systems in conjunction with our physical research studios as well. So I'm going to start right off the bat by showing you the complete mixed reality demonstration or application that I've been developing over the last few months. So this is quite a dense and involved video. So what I'll do is I'll give you an overview over it and walk you through it. Then I'm going to dissect it a bit and give you some insights into how it came together, why it came together, and where we believe as a company this type of technology and this type of research can really benefit yourselves and all the amazing research that you're doing, and really allow all of us in this community to ask very intriguing questions about the future of all things self-driving. So before I start the video, what I just want to give everyone sort of a bearing over what you're actually going to see. So this is my basement, my pandemic lab, if you will, at my house in Toronto, Canada. And what I've done here is basically provided a map, a physical map, even though there's nothing on the ground. And basically this car, as far as it's concerned, is localizing itself using LiDAR and then calibrating that to this type of map. And so you'll see that the car will drive around. This is sort of the perimeter of the map that it will drive around. And while it's driving around, there's a bunch of different systems that's implemented on the car. Obviously, I'm using the LiDAR as a means to self-localize. So that's really one great benefit that we've developed alongside our Quanser Q car. And it's also using a slew of its sensors. In this case, it is using predominantly the RealSense RGBD camera, and it's using the distance measurement to avoid obstacles, collisions, other cars, other people, obstacles in its way. So it will modulate its speed based on distance and obstacle in front of it. And then the RGB feed of that RealSense is passed on to a neural network that's classifying images. In this case, in the actual physical space, I have a slow sign and a stop sign there and a slow sign here, and the car will react accordingly to those two signs. What you're seeing down here is this is the RGB feed from the actual physical car. This is how well it's localizing and tracking based on where it believes it is in the map and where it's trying to track in terms of its trajectory in the map. Here's an idea of the speeds that are being commanded to the car. So you'll see when it sees a stop sign, it will slow down or it'll go to 0 meters per second. When it sees a slow sign, it'll go from 1 meter per second to half a meter per second, and so on. What you're seeing over here is its digital twin. It is, this is probably the first time we are publicly showing this asset, and this is part of our evolution of the research studio. So there'll be more information on this in the months to come, and I'm going to show you some examples of how to take advantage of it. But essentially, it is a complete Quanser digital twin, and akin to all our digital twins that we've released through the pandemic, it allows you a very seamless way to take code and then run your code either on the physical car or on the virtual car. In this particular example, the physical car is simply sending its location to this green car. So this green car is only a location. It's basically showcasing the location of the physical car in the virtual space, and all its it's just its position is only a direct correlation to where this car is mapping itself. And then there's also two virtual cars in this space. So obviously in my physical space I only have one car. In this complete virtual space I have three cars, two virtual ones, a yellow car that's driving at normal speeds and a red car that's driving at slow speeds, and then my green car, which is a direct digital twin or replica of the location of this car. The other benefits you'll see is here, this is a feed of what my virtual car or the green car is seeing as far as its RGBD camera, and it will also react to other things happening in the digital space, when it comes to other vehicles, stop signs, pedestrians, and so on. So let's get going. This is about a 3 to 4 minute video. Again, it's a lot of information, so I'll show you some highlights and then I'll dissect it and give you some more information over how it came together. All right, so you can see here the car is driving around. Here's how the tracking is doing. It's not bad. It's actually pretty good resolution in terms of its tracking. It's keeping to its space, and it's bouncing around a little bit because there's a resolution of the localization, but for the most part it's doing quite well. Now it's going to come around. You can see virtually there's a stop sign there. So it's stopping at this stop sign, but there's no stop sign in the physical world. But as far as the car is concerned, it's a stop sign. It's telling it, the digital space told it to stop, so it's going to stop. It's going to continue now. It should probably see a slow sign. There it is. And now you'll see that it slowed down for 3 seconds and then it'll speed back up. Then it will see a stop sign and come to a full stop. So now while that's driving, I'm going to go ahead and start the first virtual car. Just give it a second there. It should start up any minute now. I think I started it right after it passes. That's right. So you can see as it's driving around, it's still reacting to the stop sign and, both physically and virtually. So now I've started the yellow car. So the yellow car is programmed to go at the same 1 meter per second. It will react to obviously only things in the virtual or digital space, and other vehicles around it as well. And that's what you'll see. So now I started the slow car as well. So you can see my green car right now had to modulate its speed. And it's doing so because the virtual red car is communicating to the physical green car its location, and then the green car is modulating its speed. Think about it as an adaptive cruise control to sort of mimic and maintain a distance from the car in front of it. So by essence, it's slowing down as a result of vehicle-to-vehicle communication. And then you can see now it's a cascade effect because the yellow car is now behind the green car. And that's the same things are happening. And you can see all the while all the other systems are running, it is still classifying images from the physical space and reacting to other virtual infrastructure elements, for example, stop signs and other cars and so on. So this is, again, a lot of information in this video. This is the complete mixed reality application. There are many ways of doing it, and part of the benefits of working with Quanser and our systems is really your imagination is, is really the limit of what is possible. We pride ourselves on providing complete open architecture systems and the ability to really configure, especially when you get to multiple vehicles and multiple agents, really interesting topologies of communications, control, infrastructure, and so on. So we'll come back to this video. I'm not expecting anyone to, to absorb too much of it, but this is sort of how this particular application came together. So just taking a step back here, for those of you who might not be so familiar with who we are, so Quanser is an academically focused company. We've been in this business for 30 years working with engineering departments and schools across the globe, and we're very proud of our approach and our focus to academia, especially engineering academics, both in the undergraduate space of teaching and bringing very important engineering concepts to life in the lab, plus our ability to work with researchers around the globe as well, and allowing them to push the envelope of whatever particular research area that they're interested in pursuing as well. And we've been doing this for over 30 years. The company was started in 1989 by Dr. Jacob Abkarian, who was a professor at the University of British Columbia, and very quickly realized that he was teaching a control systems course, yet his students were getting lost in the mathematics. It's a very real subject of control systems. You are, controlling or governing the speed of a car or a temperature of your house. And these are very real systems that everyone interacts with regularly, yet the mathematics can get kind of scary and out of hand. So how do you ground that is by allowing them to realize and bring that theory and bring those concepts to life in a laboratory experiment. So he developed this set of original Quanser products, and over the years we've evolved that approach and that philosophy into a much broader scale of offerings. And here's a good cross section of the different types of systems that we've brought together over the years. And most specifically, through the pandemic, like I mentioned, we've released digital twins of all of our most popular products. And now what I'm going to be showcasing in this webinar is the digital twin of our self-driving car studio. And that's where things get really interesting, because you're able to take advantage of a lot of virtual and digital assets, and how do you use that to continue and develop the research, both again on the physical cars and the virtual cars as well. What ties all our products together are some of these Quanser primitives or technological primitives. So everything we do is completely academically aligned to engineering courses and research. All our systems and our hardware is completely robust, expandable, and repeatable. It's a very important part of our approach. When we provide a system, we provide the mathematics and the models behind it, and we sweat the details to ensure that every single unit, from one unit to another, from year over year, will behave and be governed by the same dynamic models, because that's, again, what allows us to make sure that students and researchers are able to make that connection from, again, the theory to the practice. We're very proud of our software architecture and approach. A lot of the systems that you're going to be seeing here, a lot of these demos are a combination of software environments like MATLAB, like Simulink, like Python, like ROS, TensorFlow, and so on. So we really take advantage of our open architecture software and our, specifically around our self-driving car research studio. We've expanded to really encompass a whole bunch of other relevant software environments as well. All our experiences are fully documented and provided for free. That's a big part of what we do. We want to give back to the community, and we want to make sure that, again, everyone has full access to our solutions. And by being part of industry, we highlight these concepts of these modern concepts of engineering, like model-based design and rapid controls prototype. Back to the question at hand, specifically, what I've been intrigued about over the years as we've developed the self-driving car, it's why a digitally connected twin, and really this this thought or idea has emerged. I've talked to a lot of the researchers as well about it, and really this is sort of my own research that I do on my own. We've had 2 years of pandemic where I'm sure as many of you have had extra time on your hands, and this is something that I like to involve myself with as well. So I'll show you some images that we are from Canada. So this is not this is a very typical experience after a heavy snowstorm. Sometimes the road signs are completely occluded or covered, and you really have to use your intuition, insights, memories of remembering, oh yeah, there's a stop sign here, or there's a traffic light there, or here's my road and the curb, and the lane markings and so on. And then just in general, as self-driving technologies, and all of us have been very intrigued by how quickly and how fast a lot of these advanced systems are coming to light, and a lot of the car companies are marketing and promoting the self-driving capabilities. Yet I'm a firm believer that we are still in its infancy, and there are going to be challenges. Just for example, just using cameras alone, there are going to be different environmental conditions where just typical computer vision applications will be challenged. It's not like they won't be able to solve it, but there are challenges ahead by using just one single source of information, or even one single sensor types of information. And really, this video highlights where some of these thinking about the mixed reality or the digital twin came to life. So through the pandemic, we worked with one of our partner organizations where they wanted to take advantage of the Quanser Q car and our self-driving car studio to put together a STEM experience for high school and lower grade and elementary students. And so we were developing this, and as we were developing it, the architecture that we deployed was that everything was governed, this whole experience, if you will, was governed by a central infrastructure. And in this case, it was, this laptop in this particular case that was broadcasting information to all the different cars, and the various cars were communicating with one another, plus with the infrastructure. But you can see here that there isn't a physical traffic light, but they're all behaving as if there is a traffic light, because in the digitally connected twin, there is a traffic light, and that traffic light state is being broadcast and communicated to all the vehicles, and it's governing it. So now, this is green this way, all just turned yellow. Now that turns green this way, and all cars can go in this direction as well. So that's an open green over there, and you'll see as that turns to yellow and red, becomes green again, and this traffic can flow this way. So this was the beginnings of where I started to look at this and say, how much more can we expand on this idea of a digital infrastructure? How can it be governed by an infrastructure that is obviously, software only, and how can that be used to expand some of this research? Here's another really good example. So like I said, we've been evolving our research studio over the last few months, and this is a prototype of an upcoming map that we're going to be releasing to add a lot of value to our research. So here I have a simple controller running on all the cars. They're not really communicating to one another. So you can see there was a mishap there, and there was a collision, and now this car got a bit of road rage and is trying to get back at that car, but it stopped right there. But these things are going to happen, and there's going to be times where, because in this particular case, I was just using the distance measurement from the RealSense camera, and in that particular collision or accident, it just simply was not looking at that particular area of the image that it was receiving. So there was a collision, and obviously these things, if you only use one sensor, these things are often going to happen, especially in environments that are not controlled, and you can't guarantee sensor performance. Things can fail and so on. So because of this type of example, that's where again our approach was, how do we enable a completely digitally connected world? So over and above the physical sensors and the physical local intelligence embedded in these systems. And of course that has to be there, and of course that's going to be a big part of the solution, and making sure that these systems drive safely and don't have collisions like we just saw. And there's other software obviously you have to, so that it doesn't go across the road and things like that. But how much more beneficial could it be if these things were actually properly talking to one another, so that every single car was communicating to all cars in its vicinity, the infrastructure in its vicinity, and how much richer could that experience be, the information be, and the safety at the end of the day, the safety and controllability and performance, if you think about it, could be if you augment all the physical intelligence and sensors on a car with what computers do really well, which is talk and communicate and share very valuable information with one another and other systems as well. So it's not just car to car, but it's car to infrastructure, so V2V and V2I. So I'm going to show you what we've put together into our upcoming virtual or digital twin release. So before we do that, I just want to highlight the architecture. So in that previous demo that I showed, and actually in all these demos that I'm showing you, this is the architecture of the code. This is based in Simulink and leveraging Quanser's Quark software that allows you to take a Simulink diagram and develop control systems and algorithms and applications in Simulink. And behind the scenes, we generate the real-time code, compile it, and then target it on the various vehicles, be it the physical car that's running an NVIDIA processor, or in the case of the virtual, it's running on the same PC that I'm using and communicating with the virtual environment that's rendered in Unreal, in the Unreal Engine. So the benefit of our approach with digital twins is that you can take the same code, in this case, what you're seeing on the screen, and deploy it multiple times on various physical vehicles and multiple times on various virtual vehicles. And that's kind of what I've been doing as well. And you'll see how that came together in that initial application. So just some more insights. This is, like I said, probably the first time we're publicly showing the virtual Q-car environment, the virtual self-driving car studio environment. And as much as we were very proud and of what we've done with Q Labs, and Q Labs is Quanser Interactive Labs, is what our collection of digital twin assets is. We've really taken it that much further with this upcoming release. And so in this case, the physical car, sorry, the virtual car mimics the physical car, so you're able to deploy code to it the same way you do on the physical car, and you can simulate all the sensors and the dynamics and the performance on the car virtually. But over and above that, because of the fact that this is a digital immersive space, an open world, if you will, all the other benefits of that are also leveraged and taken advantage of. So our team that are developing these have done a fantastic job in providing us a lot more information. So in this case, I can view each car separately, so I can see the cameras from sort of a bird's eye view for each car. But even more importantly and more powerfully, every single sensor, specifically the sensors of interest, for example, on the physical car, we have 4 CSI cameras that give you 360-degree view. Each one of those 4 cameras is rendered and simulated in this space. So you can see over here, so we have our front, left, right, and back cameras, and all of that information can be accessed through the different software environments. So you can make a call and say, provide me the camera stream from the front or the left, or my depth, or my RealSense RGB, and so on, or my LiDAR. And so this really allows for a lot of rapid development of algorithms, as much as we always believe that at the end of the day, a physical realization of these architectures and solutions is the best way to progress research and teaching. There's a lot of benefits in this digital twin, because you can iterate very quickly, you can try out different things, and in my the example that I started with this morning, you can actually put it together, and so you can now extend it. So if in your lab you have 2, 3, 4 cars, you can augment that with the same quantity, if not more, of the virtual cars. So then you can really develop some very interesting systems as they come together. Here's another example, sort of showcasing how I took advantage of the digital space to really optimize my V2V communication. So again, the same idea that I have a slow red car and a medium speed yellow and a fast moving green car. And in this case, they're governed by this traffic light. Obviously, it's a digital traffic light. But here's a good way that I was able to use the digital twin and this virtual environment to really fine tune my V2V communications and the algorithms that are governed by it to ensure that once I deploy in the physical car, it's behaving the way I expected. And I can test out a whole bunch of corner cases. There's a lot of benefits without having to have two cars slam into each other repeatedly before you can tune your application. Here's just yet another example of how to bring it all together. So back to the initial application, the mixed reality, and really, the impetus for that was for me as I started to develop these applications, and for us at Quanser as we start to look at how do we highlight the benefits of mixing the physical and virtual. The concepts of, like I mentioned earlier, I truly believe, and I believe a lot of my colleagues as well, that the more information these vehicles have, the safer they can be. The more information they can have, the more optimal the traffic flow can be, or the optimal, energy efficiency or sustainability can also be. Because if you can actually, over and above just position information or traffic, state information, you can even communicate intent, where you're trying to go, which if you're going to make a lane change, you can tell the world around you that you're signaling basically a lane change. How much beneficial is that when you're driving and you see somebody put on their blinker? It's giving you a lot of information. Computers and cars can do that much better and that much more with richer information. You can be communicating speeds and intent and when you're going to be getting off and on and so on and so forth. And you can communicate other things. For example, one vehicle could see a pedestrian, an obstacle, a hazard, and communicate that to the rest of the fleet or the systems around it. So again, all of these configurations and applications are really, this is just the beginning, and this is just one small sample of how this could be leveraged to really challenge ourselves and challenge the state of the art of where this technology can go. Hopefully what you're seeing with our approach is this is a solution, an open platform, an open canvas for you to really ask these questions and pursue these answers as well. So back to that particular example that I showed right off the bat, this is what I did. So I explained that I had this fairly straightforward code that was running, governing all the cars in terms of how it's being controlled. Drive is at the end of the day, I'm governing or modulating its speed and its steering based on a various which path it should follow and the various information. For example, if it's an obstacle in front of it, then the speed is going to be modulated, and if there's a traffic light or a stop sign, command it to a zero stop. So fairly straightforward architecture, but the benefit of it is I can take that code now and I can deploy it. So in the case of the example that I showed at the beginning, and I'll go back to it one more time, is I took that exact same code and I deployed it on the two virtual cars, so the yellow and the red. I then took that exact same code and I deployed it on my physical car in the space. And the final thing I did was I had another application that basically forced this virtual code to have the fixed position that's being broadcast from the physical car, and then any signs that I've classified in the virtual space of the analog or avatar, if you will, of my physical car was being sent back, so that a virtual stop sign would signal the physical car to stop, and so on. So we'll go back again and rewatch this initial application, this initial video, and I'll go through it one more time. Like I said, this is a very dense video. There's a lot of information, a lot of things happening in there as well. So it starts off with just a physical car driving. You can see how there's a one-to-one. So in terms of what the green car here is doing, it's simply just positioning itself wherever this car believes it is. So wherever my physical car thinks it is in this space, it's being rendered in this virtual space as the green car's location. Now, the benefit of doing this as just simply, in this example here, where the physical car and is being tied directly to its virtual avatar, is that I can place, different things in the virtual space. I can have a pedestrian walk across it and find some code to react to it. I can, as I have already here, put stop signs, in various locations, and it will classify them and react accordingly and so on. And then obviously, to me, the benefit was when I started to introduce multiple cars, in this case, two other virtual cars, but we can extend that as well, and they can all have different behaviors and things as well. Obviously, it's also, the code is still running here, where if I were to come up in front of it, it would honk at me and stop, or if it sees a stop sign, it would stop as well, same as the slow sign. So this is where things get interesting. And so I get my virtual slow car, the red car, driving. You can see immediately, the physical car is reacting as if there's a car right in front of it. So that's again the benefit of doing things in mixed reality. As you all know, there's always a challenge. As much as we can simulate and model all our systems and developing code or simulations, or developing on a simulation is very beneficial, gives you a lot of opportunities to iterate and trial different scenarios and so on. There's always a nuance when things get deployed on a physical system, and that's really where Quanser has always shined. We've always been very proud of ourselves that we allow researchers and educators like yourselves to take everything you do in the theory and in the lectures and in the research, and be able to validate, deploy, and really extend that application on a physical system. And that the same way, we truly believe this ability to now not just do things physically like we've always had for the last 33 years, but now also take advantage of the digital twin, the virtual assets that we provided. And finally, there's some benefits of mixing the two. And that's really what this application does, is, very simply mixing the two to extend some of its capabilities, some very interesting development. I noticed some things that I had to change in my code because things, don't translate one-to-one all the time, and then you have to sort of understand why and the nuances over what's happening when you go from the virtual to the physical and back. All right, so that brings us to almost the end of the webinar. I hope you enjoyed it. I hope the videos were coming through okay. We will definitely send this webinar in its totality as a recording to you once the webinar is done, so you'll hopefully be able to see the videos in more detail as you wish. But just taking a step back, as we continue to evolve our self-driving car research studio and look at extending its application, not just to research, but to elements like teaching and outreach around the same set of studio, we'll be coming up with our one-to-one map, the digital twin map with the virtual assets. So we're really excited about that. We truly believe that will have a lot of value moving forward to everybody that adopts this studio and solution. And really, if there's one message I'd love for all of you to take away, is because of our approach and our continued support of academia and research and teaching, really our goal in all of this is to allow you, as our customers, our partners, to take our studios and our solutions, and really your imagination is what's going to limit you. It's not the software, it's not the hardware, it's not the offering, but really what do you want to do with it? What are the challenging questions you're going to ask, and what are the answers you're going to strive to attain by using our solutions? So there's a lot of extended benefit. This was just a simple application of how you can mix physical and virtual together. Obviously, a lot of things that were in this application, things like vehicle to vehicle, vehicle to infrastructure, really asking questions, what are the benefits of a static fixed map? Which, again, I think even if it was just static, there's a lot, our infrastructure and roads don't change that much. So even having static information, I think is very beneficial over and above just having a very intelligent self-driving car system with real sensors and so on. Plus that idea, as we emerge through the 21st century, connectivity, digital twinning, the metaverse, all of these things of very dense digital information, I truly believe that is the right answer. But we're still in its infancy. What exactly does that mean? How does that actually come to pass? And how do you ensure that all this communication is happening, and what to do when it's not available, so on and so forth. So very exciting times. I really believe there's still so much more research, so much more development, advancement, and understanding that all of us have in this exciting space of autonomous systems, and specifically in this case, self-driving cars. And yeah, and at the end of the day, we're always blown away and impressed, and very excited to see what all of our customers, all the great research, all the great applications that our customers develop in and around our solutions. So I will end with some more interesting videos that you'll see from different things that we've done, and we look forward to you reaching out. If you have any questions, please reach out to us right on our website. You can email us at info@quanser.com, and we look forward to continuing the dialogue with you. Thank you very much.
Thank you very much, Paul, for a great presentation as always. And I think we can jump straight to Q&A. I think for a lot of our regular attendees and users, your basement lab has become a familiar scene and a lovely scene to, it's great to see how much development you've been able to achieve in your pandemic lab. And let's get to the questions, for which we do have a good number. Let's start with a question that's actually we do get it quite often, not just about the Q car, but also on our drone platform. And the question is there a dynamic model for the Q car? For applying some of the algorithms, we need to know whether we should apply for a model-based or a data-driven algorithm. For example, for fault detection algorithms. So is there a dynamic model available for the car?
That's a great question. So, the physical drivetrain, if you will, of the Q car, it goes through a DC servo motor, and we have all the, that's fairly simple to model, and we do have a dynamic model of how you can translate from, motion or voltage applied to motion. So we have that modeled, and we can provide that for sure. The steering is a little bit more challenging. It is a servo-based steering mechanism. We do have a model for it as well, but it's less instrumented. In terms of our drivetrain, we have a high-speed encoder, high-resolution encoder, so we have a very good representation of its speed. So we have characterized it on our current surfaces in terms of what is that model from voltage applied to speed. But when it comes to the steering mechanism, we have a model that we validated sort of empirically, that we also provide as well. And the benefit of our upcoming release of the virtual Q car, as you can see here in the image, is that all of those models are also embedded in the solution, meaning when you actuate the virtual car, it will behave exactly like you were actuating the physical car.
Right. I think this next question can also be looked at as somehow an extension to this, which is, what are some of the potential application scenarios for this type of work, and what's the difference between this and the development environment in Gazebo?
Yeah, that's a really great question. And for us, we want to make sure that everything we provide is able to meet the researchers where they are. And we know specifically with autonomous systems, specifically with things of this nature, Gazebo is a fantastic platform that can be used. So we will be highlighting examples using Gazebo, and then extending those to also be in our environment. So the benefit of the Quanser Interactive Labs and the approach that Quanser has taken of having our own simulation environment. I mean, a lot of this could have been done in Gazebo, and when we release our content for the teaching applications, it will also be in Gazebo as well. But the benefits of having our own virtual environment, we control the whole environment, so we've optimized the application, and B, we embed our dynamics directly in the simulation, meaning when you take that code that I showed earlier, it is a one-to-one relationship. So there's nothing else you have to do, meaning when I deploy that code on the virtual car, or if I deploy that same code on the physical car, the experience is the same. The sensor suite's the same. The interactions with the camera data, the sensors on board, the IMU, the GPS, the lidar, and so on, is exactly one to one. And so we're able to ensure that duality by doing it ourselves. But that doesn't mean that Gazebo's isn't an application that you can use. I'm sure a lot of researchers are very familiar with Gazebo, have their own code already built around Gazebo, and we will also be releasing examples that leverage Gazebo as well.
Thank you, Paul. Another interesting question. How does mixed reality help bridge the gap between simulation and the real world, especially for deep reinforcement learning algorithms?
Sorry, can you repeat the question, Pasha?
How does mixed reality help bridge the gap between simulation and the real world, especially for deep reinforcement learning algorithms?
Yeah, that's a that's a very interesting question. So just to give you, I sort of, when you watch some of these videos that I had, the incidentally that classifier, which was a deep neural network implementation, was developed and generated, sort of taught. It was trained on the physical system, and then when I send it the RGB feed from the virtual environment, the classifier was just as performant. Maybe not 100% because it was trained on a very different set of data, but it was still quite performant. So I believe the converse will also be true, meaning the benefit of this virtual space is that you can drive these cars, indefinitely, and then label your training data with, different signs, different whatever your training your architecture is, and that trained model, that deep neural network, should translate to the physical world. And I think there's a lot of research about its transferability, its applicability in the real world, but this provides a great platform to really challenge that assumption and challenge those questions. So it works both ways. and again, I've seen it in practice because I took the exact same classifier that we developed on the physical system, we trained on the physical system, and deployed it on the virtual system, and it was quite performant. So that's shows me some great ways to leverage that approach, plus validate it. Do some research about its. I say it's performant, but I didn't classify or I didn't quantify what that performance means. So was it 80% as accurate, or 99% as accurate? I'm not exactly sure, but I think these are great questions you can challenge by using the solution.
Right. Thank you very much, Paul. There's a few more questions. Another, I guess, environment-specific question. Can we use the Unity game engine for virtual representation of the car?
So what we have developed, so when you see our Quanser Interactive Labs, all of that is developed with the Unreal engine, and that was just our expertise. That's what we believed was the right approach. There's a lot of benefits of us taking advantage of Unreal. So the full application, the full simulation, the virtualization is all done in Unreal. Having said that, if Unity is what you're familiar with, then we can definitely provide 3D models of the car that you can import into Unity, but in terms of simulating it and driving it and getting the information back and forth in the same format as our current software architecture that allows for that flexibility of targeting virtual or physical or both, that's a challenge, right? So it really depends on what you mean by it, but can you use Unity to interact with a physical car or have some communications? By all means. It's just it depends. It probably requires a bit more discussions with us, and we can definitely we're more than happy to have those discussions.
For sure. Fantastic. So another question, another two questions I'll combine into one. What are the supported software environments, and more specifically, can I use Python to develop my applications?
Yeah, that's again a great question. Python is definitely a big software environment, specifically again around concepts of autonomous systems, and even more specifically when it comes to the realms of machine learning and neural networks, applied AI, and so on. So right out of the box, when we released the self-driving car research studio back in 2020, Python was a big part of that release, meaning that as much as Quanser has always leveraged MATLAB and Simulink as being the environments, because we came from robotics and control systems, and then that made a lot of sense. We know full well that other, ROS, Python, Gazebo, like we talked about, TensorFlow, and so on, are software environments or application environments where our customers are going to want to go to. So we released the self-driving car research studio with a good Python collection of support, and we released it in a way that you could use Python in conjunction with other languages at the same time. So if you had expertise in MATLAB and Simulink and another set of expertise in Python, you can combine them and use them in different applications. Actually, one of my demos have a mix of Python and Simulink as well. What you're going to actually see over and above that, when we release the self-driving car teaching content around our evolved solution, all of that will be in Python. Because when we're talking with our customers, talking with researchers, specifically the teaching and onboarding, we're being asked, can we provide that in Python? So all of that experience will be Python based, and we're really excited about how Python's going to be adopted for teaching elements, but all the while, again, all of our examples are in multiple software environments, because we want to be as agnostic as possible, and as to allow researchers to meet researchers where they are. So if you're comfortable in C++, we have examples for you. If you're comfortable in MATLAB, we have examples for you, and so on.
Thank you, Paul. And I think with that answer, you started to actually answer even the next question, which goes as follows. You mentioned teaching with this technology. What sort of teaching supporting material or courseware will be provided?
Yeah, so what we've always done, especially when it comes to cutting edge technologies like self-driving cars, we know that our market, yourselves as academics and researchers and teachers, this is predominantly in the research sphere for the most part, but because it's evolved quite a bit, and then obviously there's tons of more research and studies to be done on this type of technology. More and more customers are asking, how can I use this to teach these concepts? And so we will do what we've always done with our teaching solutions, and we have a very rich curriculum approach to it, and we please stay tuned to our website and our communications over the next few months, where we're going to release the full details of what that curriculum will entail. So at a high level, yes, by all means, we are going to have, I believe currently we are planning 10 plus experiences around, teaching experiences around the actual QCar as well. And the benefit, again, when we release this Revolved Studio, we're going to have those teaching the curriculum pieces, lab experiences, be able to be deployed on the physical car and or the virtual car. And we really believe that will allow you as teachers of this technology to really expand its usage. Because once you adopt the virtual world, then you can obviously scale to your full class, where it's more challenging doing it physically, because you want to have a car for a group of students as well. So we're going to provide the same curriculum. Again, because of our approach, you can deploy it on the physical and or the virtual, and it will behave, and the experience is just as rich with either path.
Thank you, Paul. I think I heard you mention time frame of next couple of months. There is actually a question here that says, when will the virtual version of the Q car be available?
Yeah, so our current plan is we're going to be putting together the launch material and the full studio offering as we enter the summer, and you can expect for this to be available within the summer. So we're targeting June, but things are challenging. We know we have some updated assets in terms of what's going to be provided physically, and supply chain being what it is this day and age. It's been timing has been a little bit challenging, but our goal is that this will be available as early as June this year. So a few months away.
Amazing, amazing. Looking forward to it. I have what seems to be the last question. If anybody else has any last minute questions, please feel free to send them over. But for now, this looks like the last question, and it reads, can I use the physical car outdoors?
Yeah, so it's funny because we've been talking about outdoor on a bunch of different platforms of ours. So out of the box, all of the assets, all of the experiences around our studios, the intended use is definitely in an indoor lab. Specifically, when we release this new map and this new set of assets, it is very much targeted towards an indoor university lab space. Having said that, this is, we basically, one way that I explain what the Q car is, it's a research computer on wheels, and the chassis that we picked for the car, it's a Traxxas chassis, and Traxxas is sort of the leading provider of RC car chassis in the world. They're always designed to go outdoors. So there's nothing preventing you from going outdoors. There's only things you have to consider. For example, these cars communicate to the development PC or the host PC or the ground control station via TCP/IP. So if you take it outdoors, you have to make sure you have a connection to it. We provide a joystick with the car that can be plugged in directly on the car itself, so you can use the joystick to trigger certain elements and events. So again, there's nothing preventing the car from going outside. I mean, it's built on a chassis that's designed to race around as an RC car outdoors. But there's some more considerations you'd have to take. Again, connectivity is a big one. How do you start the application? How do you stop the application? You have to think about these things a bit more specifically, because last thing you want is the car to run away on you and you're running down the road and chasing it. But other than that, there's no reason why you can't take it outdoors, and we've actually developed the car in a way that it is completely expandable. So a lot of our customers ask very typical outdoor questions like, how do we integrate GPS? And we've developed a lot of examples on how you could go about doing that and augmenting the sensors to things like GPS and other sensors that you might want to take advantage of outdoors. So by all means, it's just there's some more caveats and some more considerations you have to take to what does that mean, taking it outdoors.
Awesome. Thank you very much, Paul. I see that there are no more questions, which means that brings us to the end of this webinar. A big thank you to everyone who joined us today. Thank you so much for sharing your time with us. And for any additional information on our self-driving research studio and our other products, please visit our website at quanser.com or send us an email at info@quanser.com. If you have any outstanding questions from today's webinar, you can also send them to us via these channels. And please don't forget to follow us on LinkedIn. And with that, I thank you once again. Have a wonderful day, and please continue to stay safe.
Thank you, everyone. Thank you for taking the time. We look forward to meeting you in person at some conferences coming up soon as well. Thank you very much.